Good morning. So let's continue our discussion on Spintronics. Okay, so today we are going to learn about the origin of Spintronics and the first application of Spintronics. Okay, so as usual, we'll have OCLAB session. So please scan the QR code and log in to OCLAB. And I also want to make this announcement on the Friday, 23rd May afternoon. You will have exam. Okay, so this is part of the course. So the exam will be of 2 hours. So there will be multiple choice questions. So there will be only one right answer. Okay, so if there are A, B, C, D options, just choose one right answer. Then Saturday, the last session we'll be discussing those questions. I think that also will help me how much you have understood, so I can revise those part and we can reinforce those concepts that you didn't learn very well. Okay, so this is how it will be happening. Yes, I'll give you like 30 more seconds to scan the QR code. Okay, so let's get into the topic today. So first slide itself is a question. Okay, so before I discuss the answer for this question, let's go to the next question. Okay, so now we go to the first question. Okay, so this is very quite expected because I didn't teach you, so all of you are guessing, right? Okay, not this is not. This is the first question, for which we have given various answers. So I have mentioned many times that hard disk technology is the one which gave rise to the Spintronics principles. Okay, and hard disk technology is the first technology to use Spintronics principles, and hard disk technology typically generates $20 billion per year. Okay, so the correct answer is like let us say we just exclude whatever MRAM brings in. So, it is about $20 billion per year. So, this is the kind of impact that Spintronics has on the economy. For the next question, you should know like how long we have been using Spintronics principles. Okay. So, Spintronics technique has been used for around 25 years. Okay. This slide was prepared, I mean this question was prepared 5 years ago. So, assume 20 years multiplied by $20 billion will be 400 billion. Okay. So, this is the correct answer. So, basically these slides tell you that Spintronics is not something very new. Okay. So, for some of you, you may think that Spintronics is very new, but Spintronics has been there even before people coined the word Spintronics. Okay. So, some of the concept that I will teach you happened in 1980s, and some of the concepts have happened like even in 1800s. Okay. So, at that time we did not have the word Spintronics. So, Spintronics is not very new, and it is not like a blue sky topic, it has applications. Okay, so, it already has applications in as a read sensor in hard disk drive, and MRAM is a new application. Okay. So, today we will be learning about how we can sense information using Spintronics principle. So, this is some slide that I gave you on the first day. I told you that in conventional electronics we only utilize the charge property of the electrons, because all the elements in the conventional electronics are like silicon, copper, wiring and so on, which are based on non-magnetic materials. On the other hand, in Spintronics we will be using magnetic materials. So, we are going to use the spin property of the electrons. Okay. So, when you have magnetic materials and you send electrons through magnetic materials, there is an interaction between the spin and the magnetization of the magnetic material. As a result, the electron flow will be spin dependent. Okay. So, we are using this spin dependent property in Spintronics. Okay. So, this is something that I introduced on the day 1. Okay. So, I told you that Spintronics has been used for around 25 years now. So, if Spintronics wasn't there, for example, the hard disk that you buy may have a capacity of 100 gigabyte. Okay. Now, you are easily buying 10 terabyte, but if Spintronics wasn't there, maybe like 50, 100 gigabyte or so, okay, not more than that. So, hard disk drives would have a very low capacity. So, probably we will be still using DVDs to store information, or flash memory would have taken, and we would have no application like YouTube, Facebook, things like that. And more importantly, all those movies that you see with a lot of computer graphics wouldn't be possible. Okay. So, to give you one example, James Cameron made Titanic movie in 1997. So, at that time itself he had the concept of Avatar. Okay. So, 1997, from 1997 until 2009 he didn't release any movie, okay, around 12 years. So, he was waiting for this Avatar movie to be made because the technology wasn't ready. Okay. So, to give you a reason why, for example, so when you shoot movie, you generate lot of digital data. So, I told you that if you shoot movie in certain format, you need so much terabyte per hour and things like that, right. So, to shoot a movie like Avatar, you need like 1 to 2 petabytes of information. Okay. So, you need hard disk drives with this kind of capacity. So, in 1997, the highest capacity of the hard disk drives was like only 500 megabyte. Imagine, it is not even 500 gigabyte, 500 megabyte was the typical capacity. So, around 2006-7, at that time we could make like 300, 400 gigabyte hard disk drives. So, storing lots of information in 1 petabyte was possible only around 2007. So, that is about storage. then we also need to talk about memory and so on. So, all those technologies were not ready to make a movie like Avatar, and only like 2007 or so hard disk drives were enough to shoot movies like this. Okay, now we have an overdose of CGI movies. I hate, they don't have any storyline, just all nonsense. Okay, so this is also another impact of Spintronics. So if Spintronics wasn't there, maybe probably we wouldn't have all those Marvel, DC movies. Okay. So it's also good to know how the technology and science progress hand in hand. So science is like a tree which bears the fruit. Okay. So scientific discovery, let's say scientific discovery is a seed. Okay. So it takes time to grow and give fruit. Okay. So fruit we can say is a technology. Okay. So you can see here the scientific discovery and the technology, how and when happened, when it happened. So we can see, for example, in the 1800s people were studying electricity. So they knew that charges are responsible for electricity, but they didn't know about electrons. Somewhere in 1900s electrons were discovered. Then people used these electronics, I mean they started building electronics. So the first electronics was based on vacuum tubes. Okay. So they have a tube with the anode, cathode, grid and so on. So they could control the flow of electrons. Then we had vacuum tubes. So these vacuum tubes were useful in the World War I, II and so on. Okay. So this is like when electron was discovered and when they were like used really. Then if you take spin, for example, the concept of spin happened somewhere in 1925. Then people came up with some theoretical model, and one of the discovery based on spin was giant magnetoresistance. This happened in 1989, and after 11 years people could make some sensors based on the giant magnetoresistance, and they can use it in hard disk drives. So since 2000 we have been using, I mean even before that we have been using some Spintronics heads for reading information. That's one thing, that's about spin. Then there are some concepts that you will learn later, spin transfer torque and so on. So this spin transfer torque was discovered in 1996. Okay, so 1996 spin transfer torque was discovered, but people started using this concept for technology somewhere around say 2018. So around 20 years it took to make use of this discovery. Then around 2012 there are a lot of research papers on spin orbit torque. Okay. So this has not yet made into a technology. Spin orbit torque is not yet a technology, but it's going to be useful somewhere in the future. So you can see that the discovery happened sometime, then at some point of time some technology comes into picture. Okay, so here I will say the story of Spintronics. So in the late 1800s, late 19th century, so people thought that everything in physics has been done. Okay, so the Newtonian mechanics was there, then Maxwell's laws were there. So people thought that they understood everything. So it was said that Lord Kelvin, he even mentioned that there is nothing in physics to be done, only some fine tuning of physics we need to do, something like that. Okay, but you know that in early 1900s, so many new observations were coming, black body radiation, spectroscopy, so many things came at that time that led to the revolution called quantum mechanics. Okay. So when you talk about spectroscopy, it was coming into picture. So, people were expecting, say for example, spectral lines at this position 1, 2 and 3. This was supposed to be the theoretical spectral lines, but when you do experiments, people observed that there are some fine splitting. Okay. So, instead of one line here they saw two lines, again instead of one line they saw two lines and so on. Okay. So, there are some fine splitting happen in the spectral lines. So, experimentalists blamed that this is theoreticians blamed the experimentalists. They said this is experimental error, this is not possible. However, this guy Goldsmith, okay, by the way, you go to this website, you can look at his lecture. Okay. So, he has a talk which is like a story of how he came up with the concept of spin. Okay. So, in that lecture he tells that before even he knew these results, he had done some calculation and he came up with the concept of spin. But once he saw these results, then he realized that his derivations fit into this picture very well. Okay. Then he discussed with another colleague called Goldsmith and another one who is that, Uhlenbeck. Okay. So, this Uhlenbeck is the one who gives the name spin, and he, according to Uhlenbeck, he says that electrons have some angular momentum, electrons are spinning, and he proposed, these two together propose this and get it published. Then people didn't believe. So, because electron cannot rotate, because electron's rotation will be violation of the physical laws. So, people didn't believe, but at around same time this Stern-Gerlach experiment happened. Okay. So, before I explain this Stern-Gerlach experiment, so I want you guys to do one experiment. Okay. So, here I have a fidget spinner. Okay. So, this fidget spinner, see, I can easily flip. Okay. I challenge you. You rotate the fidget spinner like this, then try to flip. Rotate very fast. Stand up, come here. Rotate very fast. It's not enough. No, rotate very fast. Okay. Okay. So, I can easily flip, right? But he cannot flip. Why? Yeah? Angular momentum. Okay. So, when I flip, this fidget spinner doesn't have angular momentum, but when I rotate, there is an angular momentum, say either pointing this way or the other way. So, when there is an angular momentum, you need a huge torque to change the angular momentum of this spinning object. Okay, with our wrist power, we cannot provide that much torque, so we cannot change the angular momentum. So, let us say even if you hold the fidget spinner like this, you try to change the direction. Say, tell me what you feel. Rotate very fast. This speed is not enough. Do you feel something? Okay, someone else try. What do you feel?
It's not as easy to just.
What do you feel? Yeah, you will feel some force on your thumb because you are changing the angular momentum. So, there is a torque, by equivalent version of Newton's third law of motion, there will be, you will feel a kind of force on your fingers. Okay. So, what this whole experiment tells you is that if something has angular momentum, it is difficult to flip, if there is no angular momentum, it can be easily flipped. Okay. So, having known this concept, now let's get into this Stern-Gerlach experiment. Okay. So, in this experiment they are sending electrons through two magnets, I mean two poles of a magnet. These poles are designed in such a way that the magnetic field lines are more in one pole. Okay, so, you see that the magnetic field lines go from this pole to the other pole. You can notice that the field lines are more here, right. So, if you count the number of field lines in this area, you will find more lines. The same you find here, you will find less line, which means the magnetic field is larger here and less here. Okay. So, let us say you send electrons, and if electrons are only magnets, so if you remember on the day when we learnt magnetism, I told you that electrons are like tiny magnets. Okay. So, if electrons are like only tiny magnets, when you send them through this, so let us say this is north, there is one electron going with the south pole here. Okay. When it comes in this vicinity, it will rotate, the south pole will go and stick here, because the magnetic field is strong here. So, all the magnets will be attracted here. Okay. And if electrons are only magnets, just magnets without spin, for example, then they will just rotate the pole and they will finally reach here. So, you will see nothing here if you think electrons are only magnets with no angular momentum. Okay. On the other hand, experimentally they found that there are electrons in both directions. Okay. There are some electrons in this region, some electrons in this region, and this concludes the point that electrons have angular momentum. Okay. So, let us say electrons have angular momentum, like this fidget spinner we could not flip, right. When the fidget spinner was rotating, we could not flip. So, they have angular momentum. So, this, let us say I told you in one case, for example, this south pole will flip and go here, that cannot happen because they have an angular momentum. So, they cannot flip with this kind of force. So, they will still continue to go along this direction. So, because of the angular momentum nature of electrons, you will see electrons in both sides. So, you will see two patterns corresponding to spin up and spin down electrons. Okay. So, this is what they observed in the Stern-Gerlach experiment. So, they saw electron pattern on two direction, indicating that electrons have spin. Okay. So, why electron cannot spin is like when you are talking about spin, for example, this fidget spinner, right, there is a center, and outside this center there are so many tiny particles, right. So, because of that we can have some spin, angular momentum, but electron itself is a fundamental particle. So, it cannot rotate around its own axis and so on, and again the speed of rotation will exceed the speed of light and things like that. Okay. So, that is basically a very brief introduction to spintronics. Now, we move on to learn how we can use these spintronics principles to sense information. Okay. So, you would have learnt about many types of sensors. So, what does sense mean? So, in electronics, sensing means knowing, I mean converting a physical property in the form of an electrical current or voltage. Okay. For example, if you take a digital thermometer, so in the case of a digital thermometer, you may have some resistor, let us say platinum resistor. So, this resistance will change as a function of temperature. Okay. So, you keep the thermometer at certain temperature, say T1, the resistance will be R1, T2, the resistance will be R2, T3 resistance is R3, and so on. Okay. So, by knowing the resistance, by measuring the resistance of this element, we can convert resistance into temperature. Okay. So, there again you are measuring the resistance because you are sending a current and measuring the voltage. Okay. So, sensing is basically converting a physical property into an electrical current or voltage. Okay. So, in the case of magnetic recording, we learnt yesterday that the magnetic media produces magnetic flux, and we are sensing this flux. Okay. Flux or magnetic field, we can say magnetic flux or magnetic field. So, we are converting this magnetic field or flux information into some form of voltage. Okay, so, that is what the sensors in hard disk drive does. So, it converts the magnetic field or flux line information into voltage. Okay, so, in a hard disk drive you have many disks and the disk is rotating, and here you have some sensor. So, this sensor flies over the disk medium. Okay, so, we learnt that this kind of north facing each other will produce some magnetic flux and so on. So, this sensor will convert those magnetic flux lines into voltage. Okay, based on some principle, you will get voltage pulses as a function of time. Okay, so, the flux that comes from the recording media is converted into voltage. So, that is what the sensors that we are going to learn are doing. Historically, the sensors for hard disk drives were based on the Faraday's law of induction. Okay. So, when we learn about VSM, okay, here we can say Faraday's law. So, when we learnt about VSM, vibrating sample magnetometer, I told you that if there is a time varying flux and if there is a pickup coil, the pickup coil will pick up a voltage which is proportional to the time varying flux. Okay. So, this is something that we learnt already. So, until 1990s we did not use Spintronics principle. Okay. So, we use this simple Faraday's law to sense information. Okay. So, forget about this for the time being. Okay. Just look at this one. So, this is an electromagnet. By sending current through this, we produce some magnetic field and we use this head for writing information. Okay, so, you can see that the material is magnetized in this direction or in the opposite direction by changing the current direction of this electromagnet. Okay. So, this is the writing element. And until 1990s, people used the same writing element for reading also. Okay. So, for example, if you look at this, this is a pickup coil. Okay. So, this pickup coil will convert the time varying flux into a voltage. So, you can use, if you connect some voltmeter here and if you move the disc media below this, you will see voltage signals. Okay. So, we use this Faraday's law to read information until 1990s, but that was like there were many problems. For example, we learnt yesterday that MRT is responsible for signal, right. MR is the remnant magnetization, T is the thickness of the film. So, the product of these two gives rise to signal. So, you might say that if you increase this, you can increase the signal. Okay, that is a very simple thinking, but there are other problems. I did not go through the details yesterday. For example, if you make the MRT very large, the pulse width also is going to be very large. Your pulses will be very large, which means you cannot pack information at high density. So, pulse width, if your pulse width is large, your density will be low. Okay, so, to understand this one, let us recall the cheat sheet example. Okay. So, in your exam you can take a cheat sheet. So, you want to write the material for the exam. So, which pen will you use? You will use a pen with this kind of tip or sharper tip? Sharper tip, right. So, with sharper tip you can write fonts, small fonts. Okay. So, small font is like having very small PW50. A tip like this will produce very big letters, which means large PW50. So, we don't need a large pulse width, we need smaller pulses, but with large MRT you will have large pulses. So, you cannot achieve high density. With large MRT you can have high signal. Okay. So, people do not go to increase MRT, they try to reduce MRT to make the pulses narrower like this. They want sharper pulses, so they can pack density, I mean information at high density. So, the problem of these inductive sensors were they did not get sufficient signal. Okay. So, when your MRT is low, the flux that you send out will be low. So, it is like if you have a big magnet, it will send more flux line at certain distance, but if you have a small magnet, the let us say here for example. So, at certain point you will see more flux lines, whereas this will give only a few lines. Okay. So, when MRT was reduced, these inductive heads did not produce sufficient signal because the flux lines which were reaching this head were fewer. Okay. So, that was a problem, but hard disk drive was driving, I mean it was going smoothly until 1990s with this technology. Okay. Then in 1990s hard disk drive started using something called anisotropic magnetoresistance based heads. Okay. Then at that point of time the reader was separate, I mean there was a separate read sensor and they had a separate write sensor. So, writer. Okay. So, that is what is shown here. So, here now after this discovery of anisotropic magnetoresistance, after introducing anisotropic magnetoresistance, people had one sensors based on anisotropy magnetoresistance for sensing, and another writer. Okay, so we can say that from 1990s, the heads used in the hard disk drive have two parts. Okay, one part is for reading information, another part for writing information. Okay, so this is the configuration we use since 1990s. Okay, so one set of researchers focus on how to improve the writer, and another set of researchers focus on improving how we can improve the sensitivity of the readers and so on. Okay. So, this is a real life chart of how technology has produced and what were the contribution of Spintronics, for example. So, until here people were using the inductive head. So, I told you that we have been using inductive heads since until 1990s. So, the growth was like 25% every year. Okay. So, for example, if I have 1 gigabyte this year, next year will be 1.25 gigabyte and so on. Okay. So, 25% increase every year until 1990. Okay, so this is the year the industry used first magnetoresistive head. Okay, after they introduced the magnetoresistive head, you can see that the growth has increased to 60%. Okay, that means if the capacity was 1 gigabyte earlier year, now we will have 1.6 gigabyte. Okay, you can see the difference. Then at some other point of time, say around 2000, people introduced GMR head. So, you will learn all this terminology later, but I am just giving you some data. After you introduce GMR head, you can see that the growth is 100% every year. Okay. So, for example, if the capacity was 10 gigabyte this year, next year it will be 20 gigabyte. Okay, it has almost doubled. Then later it will be 40 gigabyte. So, after people introduced the GMR head, the capacity was doubling every year. Okay. So, this is the impact of Spintronics in the hard disk technology. Okay. By bringing in Spintronics based sensors, we have improved the sensitivity of reading information. So, we could double the capacity for many years. Okay. Every year we were doubling for many years. So, these are the impact of Spintronics. Okay. So, now let us move on to learn about the, I keep saying AMR, GMR and so on, but we haven't learned what is magnetoresistance, right. So, we will start in a simple slide. So, you take a piece of wire, you apply some electricity, then you will notice that the electrons move from one side to the other side depending on the electric field you apply. Okay, so, the tiny particle that you see are the electrons. So, you can see that they drift. Okay, so, here I want to ask you this question. So, I am saying a snail may travel faster than electric current in a wire, copper wire for example. True or false? Okay, majority of you are right. Okay, snail may move faster than a current in a current carrying wire. Okay, so what happens when you have a conductor like copper, for example? You don't apply any electric field, you don't apply any voltage. Then what happens is that the electrons inside the copper wire, they will undergo random thermal motion. Okay, so they will go from so electron is here, it may go here, 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 something like this. It will undergo random motion, but the center of if you take the average position, is somewhere here. Okay, so with respect to this position, it is going here and there. So typically this kind of random motion happen because of the collision of electron with say some phonon, scattering from phonon defects or other electrons causes this kind of phenomenon, and the typical distance before it undergoes a collision is around 1 to 10 nanometer. So the mean free path of electron is around 1 to 10 nanometer. So this is important, you note this point. Okay, and when you have like only the temperature effect, the typical velocity of these electrons is around 10 power 6 meter per second. Okay. Now, let us say you apply certain potential. Okay. So, you apply electric field, then again the electrons undergo this scattering. Okay. All these things still happen, but because of this electric field it is drifting. So, here the center was at one position, average position was somewhere here, but when you apply electric field, the average position moves from this point to this point, but still the electron is undergoing all this scattering. Okay, it slowly drifts. So, this is what we call drift velocity. So, typical drift velocity of electron is around 10 power minus 3 meter per second. Okay, it depends on the current density that you apply and so on. So, if you look at the speed of a snail is 13 centimeter per second, and the drift velocity for this will be actually very low, around 0.5 millimeter per second. If you apply very high current density, yeah, you can make the electrons move faster, but for typical current densities, the speed of electron along this direction can be lower than the speed of a snail. Then you may wonder, how come we switch on the switch and we can get the light immediately? The electricity appears to travel faster, right? So, for that you can take a water pipe analogy. Let us say you are living in your home and you have been living there for many years. Okay. So, you open the tap, you will get water immediately. Okay. On the other hand, let us say you move to a new house, you have a water tank on top of your house, water tank just got filled, then you open the tap in your kitchen, then you will realize that the water takes some time to reach. Okay. It has to travel all the way through the pipe, then it takes some time to reach you. Okay. On the other hand, if the pipe is already filled with water, the moment you open the tap, you will get the water immediately, right. So, in a similar sense, you can understand that the copper wire is filled with a lot of electrons. Okay. So, it is like a filled water pipe. So, your copper wire has a lot of electrons already. So, once you apply electric field, these electrons move here and these electrons move here and so on. So, you will notice that the electricity travels faster. Okay. Anyway, the most important part of this slide is that when electrons travel across a conductor, you can see that the electrons get scattered, and the resistance of material is caused by the scattering of electrons. Okay. So, how can you measure resistance? You can use a few techniques like 4 probe technique or van der Pau techniques. So, in a 4 probe technique, let us say this is the material we want to measure. So, we have 2 probes through which we send current. Okay. So, electrons flow and we measure the voltage somewhere in between these 2 points. Then we divide the voltage by current, we get the resistance. Okay. So, this is how we measure resistance. And when you talk about magnetoresistance, what we do, we measure the resistance of a material at various values of applied magnetic field. Okay. So, you apply different magnetic field, for example, no magnetic field, you get some data. You apply say 1 Tesla, you get some data. So, like that you keep changing the magnetic field, measure the resistance of the material, then you notice that the resistance depends on the applied magnetic field. Okay. The resistance of the material that you measure depends also on the magnetic field. Okay. So, this kind of change of resistance of a magnetic material as a function of a magnetic field is called magnetoresistance. Okay. So, this is what you are going to learn. So, today I will not go into the theory. Today I will focus on how we can use the principles of the AMR, GMR and TMR, how we use them for reading information. Okay. So, the first topic that we are going to learn is anisotropic magnetoresistance or AMR in short. Okay. So, we learnt, I mean you are familiar with this word now, right. You know what is anisotropy now. Anisotropy means you measure certain property, the property is different in different directions. Okay. So, when we talk about anisotropic magnetoresistance, we are going to talk about some form of magnetoresistance which depends on the direction of something. Okay. What is the direction that we are going to talk about here, that is shown here. Okay. So, in this case we are going to talk about the direction or the angle between the magnetization and the current. Okay. So, you are applying current in the x direction. Let us say your magnetization is at certain angle theta with respect to the current. Okay. Then the resistance you measure will be different depending on this theta. Okay. So, if magnetization is in the same direction as current, you will have one value. If magnetization is perpendicular to the current, you will have another value. Okay. So, here the resistance is anisotropic based on the direction of magnetization with respect to the current. Okay. So, in the first case, magnetization is parallel to the current. So, we call this rho parallel because magnetization and current are parallel. So, we call it rho parallel. So, when these two are parallel, the theta is 0. So, you notice here that when theta is 0, the resistance is high. Okay, in the second case, the magnetization is transverse or perpendicular to the current. So, we call it rho perpendicular. So, rho perpendicular is like the angle is 90. So, here we have rho perpendicular, and for intermediate values of theta, your resistance is somewhere between this high and low. So, if you plot the resistance of this particular, so here we are talking, I mean this blue is a magnetic material. Okay. So, I do not need to say, but I will still say. So, the blue color material is a magnetic material, and we are looking at the direction of magnetization with respect to the current direction. Okay. So, if I measure the resistance of this magnetic material as a function of theta, where theta is the angle between current and magnetization, I will have this graph. Okay. So, when the current and magnetization are parallel, resistance is high. When the current and magnetization are perpendicular, resistance is low. Then for intermediate values, you have certain property like this. Okay, so here this graph is normalized by dividing by the perpendicular resistance. Okay, so the absolute values may be like, let us say this may be 600, something like that. Okay, this may be 500, something like that. The absolute values of resistance may be like 600 ohm here, 500 ohm here, but this graph is plotted by dividing all the data by this value 500. Okay. So, that is why you have a graph which goes from 1 to 1.02, something like this. Okay, so, from this measurement we can also define a parameter called AMR coefficient. So, AMR coefficient is the difference between the high and the low resistance. So, for example, 600 minus 500 divided by the low resistance, okay, 500. So, this will be 100 by 500, something like 0.2. Okay, so, these values are rubbish. Okay, do not take these values for granted. So, typically this change is only like 0.02. Here I have exaggerated too much. So, this delta rho for the best material is only around 2%. Okay, so, in terms of percentage it is only 2%. So, it is like this 0.2 is 2%. Okay. So, these values are not very correct, but I am giving you just for some understanding. Yeah.
What is the origin of this difference of resistance between?
Okay, for the AMR, right? The theory I am going to cover another day. Yeah. So, today I will focus on the how we can make use of this principle. Okay, so, this is an experimental result from our lab. So, in this case we have a wire, you can see that there is a wire of permalloy. Permalloy is an alloy of nickel and iron. Okay, so, on this wire we send current through this wire and measuring the resistance. Okay, by applying, okay, this is the wire, right. So, if I do not apply any magnetic field, where will the magnetization point to? Yeah, the magnetization will point along this direction. Why? Because of shape anisotropy. Okay. So, this is a narrow wire. So, you know that in narrow wire the easy direction is along the length. So, in the absence of magnetic field, magnetization will point in this direction. So, when the field is 0, magnetization is parallel to current. Okay, so, we know that when magnetization is parallel to current, the resistance will be high. Okay, so, we just learnt that when the magnetization is parallel to, so this theta is 0, resistance will be high. Okay, so that is what you see here. Now, let us say I apply magnetic field along the direction of current. Okay. So, my magnetic field also is along this direction. So, if I increase or decrease, so either I am going to make the magnetization along this direction or in the opposite direction. So, in all the cases the magnetization is going to be always along this line parallel to the current. So, when I measure the resistance of this device, when current is parallel to field, this value is very high. Okay. Because the magnetization is either pointing along this direction. If I apply magnetic field along the opposite direction, it will flip to the other direction. So, current and magnetization are always 0. So, the resistance is always high. So, that is what you see in the blue curve here. Okay, so, this line is basically when the field is parallel to the wire. Okay, now let us consider the other case when the field is perpendicular to the current direction. So, in the absence of any field, magnetization is in this direction, resistance is high, but once I apply magnetic field in this direction, magnetization will rotate along this direction. Okay. So, we learnt that when the magnetization and the current are perpendicular, okay, when the magnetization is perpendicular to the current, the resistance will be low. Okay, so, once I increase the magnetic field, I am tilting the magnetization from the easy direction to this direction of the applied field. So, the resistance drops. Okay. Okay, so, this is what happens when you try to measure the magnetoresistance of a material as a function of magnetic field. You can change the magnetization to be either parallel to the current or perpendicular to the current. So, in this case the magnetic field changes the magnetization direction from easy direction to the hard direction and so on. So, we see changes in the resistance. Okay. Yes. Okay. Will the wire not be in demagnetized state without applying any field? Yeah, possible. In the demagnetized state also, still the magnetization will be like parallel to the, I mean you may have domains. So, some domains magnetization will be like this. Okay. So, you will have different directions, but still magnetization is parallel to the current. So, you will have high resistance. So, your demagnetized state will be still like this. Okay. Something like this. So, again you can say that all these magnetization are parallel to the current direction. So, the resistance will be still high. Okay, this slide explains why, how, we will discuss this later. But now we will move on to learn how we can make use of this principle, anisotropic magnetoresistance, for sensing information. Okay, so for sensing information, you need, okay, the best material for anisotropic magnetoresistance is permalloy. Permalloy is an alloy of nickel and iron. So, typically 80-20, somewhere there. Okay, there will be some changes in the composition, but somewhere there. So, this is the best material. So, if you want to make a reed sensor based on anisotropic magnetoresistance, so what you will do, you will make a permalloy wire patterned into some shape like this. Okay. So, the shape of the AMR element here will look something like this. Okay. Then you have two probes. So, you send current through the probes, then you measure the voltage. Okay. So, you use these two probes for measuring the resistance of this AMR element. Okay, so as we just saw in the previous graph, when there is no magnetic field, magnetization is along certain direction, but when there is a magnetic field, the magnetic field influences the magnetization direction. So, there will be a change in the resistance, and we are using that change in the resistance to sense information. Okay. So, later I will ask.
आपको महंगा मिलेगा क्योंकि वो बहुत ऊपर है, तो आपको 4045 मिलेगा.
Not here, right? Okay. So, later I will discuss you exactly what angle I will ask you some question later. Basically, you have a sensor, you have a MR sensor, anisotropic magnetoresistance sensor, and it sees some magnetic flux. The magnetic flux is coming from the recording media, and this magnetic flux changes the magnetization direction. As a result, you will see some change, and that is what you are going to read as the information. Okay. So, when people design AMR head, they place this AMR element between two shields. So, you can see that there is one shield here, then there is another shield here. So, these shields are soft magnetic materials. Okay, so, these soft magnetic materials have a property of permeating all the magnetic flux into them. Okay. So, let us say if you have a magnet here, right, magnet here, this magnet produces certain magnetic field. Okay. So, in the absence of any other material, the magnet of, the magnetic field of this magnet will look like this. Okay. On the other hand, if I place a soft magnetic material here, so all these flux lines will go through the soft magnetic material. Okay. So, this is what we learned before briefly, not much. I mentioned the term permeability. So, soft magnetic materials have a tendency to collect all the magnetic flux through them. Okay. So, that is what the shields do here. So, look at this picture. So, here you have the recording media. So, you have written bits. So, some of them are pointing left, some of them are pointing right, and so on. Okay, so, here you see there are two like poles. So, they produce some magnetic field. Then here again you have two like poles, there is some magnetic field. Here again you have two like poles, and so on. Okay. So, there is magnetic flux lines coming out from many different bits. Okay. But you want this sensor to read the bit directly below it. Okay. You do not want this sensor to respond to the neighboring bit. Okay. So, what we do? We pass all this magnetic flux from the neighboring bits into the shield. Do you understand? I do not know if you get it or not. Okay, we have lot of bits. Okay, let us say there is one bit here, it produces certain magnetic flux. There is another bit here, let us say this one, we have 0, no flux, 1, there is another 1. Okay, so we have a lot of bits. So, from this region we have magnetic flux coming out. Okay. So, now my reader is coming, let us say the reader is supposed to read this bit. Okay. So, when you want this reader to, this is a AMR reader, when you want this reader to read this particular bit, it should not see the magnetic flux from the neighboring bits. Okay. So, we do not want this to interfere when it reads this bit. Okay. So, what we do? We do not let this field come here. So, we let this magnetic flux go through this shield. So, this shield basically sucks all the magnetic flux into it. So, none of this magnetic flux go into this region.
What is the typical distance between those two seals?
Pardon?
Those two seals.
Uh-huh.
The typical distance between those.
What is the distance between these two shields, right? In some of the technology 10 years ago, maybe around 30 nanometer. So, it is very narrow.
At that time the bit size was same 12 to 13 more than that.
Yeah, around that. Bit size, when the bit size is around 30 nanometer, we have this kind of spacing, yes.
So, bit size will always be the distance between two seals will always be smaller than the bit size.
Somewhere there, almost similar kind of thing.
So, if the bit size is smaller, then they can detect 2 bits at a time.
Yeah, yeah. So, if this is very large, right, let us say this is 100 nanometer, then you cannot read 15 nanometer bits. So, if you want to read 15 nanometer bits, you have to make them closer, like at least around 20 nanometer or something like that. Okay, so, the purpose of the shields here is to minimize the influence of the magnetic field from the neighboring bits. So, because of these shields, nothing comes to this region except the field from the bits directly below. Okay. So, as an analogy, you can say that this is like the blinder we use for horses. Okay. So, horses have blinders, right? They do not see this side or this side, they only see straight. So, in a similar sense, this MR sensor only sees the magnetic flux directly below it, not from the neighboring bits. Okay, but this technology did not last long. So, it was introduced in 1990, around there, then until 2000. Around 10 years people used this AMR technology. After that we had GMR. So, why this technology was used only for a very short time is because of these reasons that I have shown here. So, for example, let us say you make a AMR sensor where the permalloy layer thickness is 10 nanometer. So, at 10 nanometer you have like 2% AMR. Now, I want to make the AMR smaller and smaller. Okay. So, as we discussed before, we want to make the bits are smaller. So, we want to go from this dimension to this dimension. So, we need to make the AMR element also thinner. Okay. We want to reduce the shield to shield spacing because the bit length is going to be reduced. So, when you want to make this closer, AMR element thickness has to be reduced. Okay. So, when AMR element thickness is reduced, okay, you can see when you go from 100 angstrom to 10 angstrom or 10 nanometer to 1 nanometer, you will see that the magnetoresistance is also decreasing, okay, which is not good because your delta R is small. When the delta R is low, let us say you send some current through the sensor to sense, the voltage change you see also will be low, delta V will be low. Okay, so, because of this reason people moved away from the AMR technology to GMR technology, then magnetoresistant technology. Okay, let us do some question. There is one tricky question. So, after I ask you that question, I will discuss some more. Okay, I will stop here, there is no timer. Okay, majority of you are right, but still many of you are wrong. Okay, what determines the AMR is the angle between magnetization and current. Okay. It is not the magnetic field versus current, it is the angle between magnetization and current. So, if you remember the slides, I showed you clearly that it is the magnetization and current, angle between magnetization and current. See here again, it is the angle between magnetization and current. Okay, next question. Let us say you want to use a AMR sensor for reading information. Okay, so, this is the AMR sensor you have prepared. Okay. So, now we are not applying any magnetic field. So, in which direction you will keep the magnetization? Okay. Let us say this is 0. I mean, let us say if the magnetization is along this one, let us say we call it 0. If the magnetization is along this direction, we call it 90. So, in which direction you will keep the magnetization, which angle you will keep the magnetization when there is no magnetic field? Okay, that is the question. Okay, there are various answers. So, before I tell you which is the correct answer, let us take a imaginary material. Let us take some imaginary material A. Okay. When you measure the resistance or voltage of this material, for example, let us call it resistance as a function of temperature. Okay. Its behavior is like this. Okay. And you want to use this material A as a sensor for measuring temperature. Okay. Which region will you operate? Let us say I say this is the region A, the region B, the region C. Region B, right? Why?
Close to linear.
Yeah, so because this region is close to linear. Okay. In the other region, your change in resistance is not proportional to temperature. Here you have some kind of linear region. Let us say this is room temperature and you want to measure from say 0 to 100 degrees Celsius, then this region is good, this is good, right. So, in this graph where you see linear region, somewhere here, right. Somewhere here is the region, I mean linear region. So, you will usually operate around this center. Okay. So, the correct answer for that question is the theta is 45 degree. So, in the absence of any magnetic field, your magnetization is at 45 degree angle, current is along this direction. So, direction between angle between current and the magnetization is 45 degree in the absence of a magnetic field. Okay, let us say there is some magnetic field going in this direction. So, that magnetic field will force this magnetization to go like this. Okay. So, you will go from this to this. Okay. So, this is now field 0. So, when the magnetic field is up, so magnetic field pointing up will make this go 90 degree. So, you will see low resistance. Okay. Now, let us say there is a magnetic field pointing down. So, this pointing down magnetic field will rotate this magnetization this way. So, it will make the current and magnetization to be parallel. So, we will go this side. So, remember in magnetic recording we have only two types of magnetic field, right. So, one like you have north pointing up, magnetic field going up, another case south pointing each other, magnetic field going down. So, we have only two fields. So, these two fields either should make the resistance to be low or high. Okay. So, we in the absence of any magnetic field we keep the magnetization at 45 degree, and one type of magnetic field will make it like this, another type of magnetic field will make magnetism to be like this. So, we will go between high and low resistance. Okay. So, the correct answer for that question is 45 degree. Time for tea break. Yeah. So, the next topic, okay, here the correct answer is 45, only 5 of you are right. Okay, so the next topic will be GMR, the end magneto resistance. We will cover after the tea break.